Alright, so we have some multiple choice questions on Chapter 3, and we have the second derivative here, and it's asking about inflection points. So remember, we have an inflection point when, because f double prime of x changes signs, and f of x is defined. Remember, an inflection point is an actual point that exists. So now, since the second derivative is a polynomial, that should mean that if we integrated back 2 steps, that would still be a polynomial. So all the points should be defined. So you can do a sign chart on this and check that, but you also should understand multiplicity. So we have 0 and -1 and 2. So -1, 0, and 2. Okay. And if we test those points, so -3, this would be negative, this would be negative. This is always going to be positive. So a negative times a negative is a positive. Then if we tried -1/2, this is going to be negative, this is going to be positive. So a negative times a positive is negative. Like I said, this is always positive, so I didn't even test it. 1, both of those are positive, so that's going to be positive. And then 3, everything is still positive. So our clue there was this squared here. Back to pre-calculus, maybe algebra 2, when you have an even multiplicity, the function does not cross the axis. It just touches and then it goes back. So that's a clue that we're not going to get a sign change when we have an even exponent on here. So it's just going to be -1 and 0. And you can see there's one with the 2 in it, but that's not going to work. Okay, so if we move on to the next one here, differentiable function, the function is always negative, and the first derivative equals this. Which of the following must be true? So this derivative, if we think about it, we're going to have x plus 2 and x minus 2 times g of x. So they're talking about minimums and maximums here. So when we want to find minimums and maximums of f, we want to see where the derivative, where f prime changes sign. So if we do a sign chart on that, we plug in -2 and 2, and we test those intervals. Now the key here is to realize that g is always negative. So this is always going to be negative. So we need to factor that in when we test points out here. So we plug in a -3. This is negative, and this is negative, and this is negative. So 3 negatives multiplied is going to give us a negative. Now if we plug in 0, we have a positive and a negative, and this is always negative. So a negative times a negative is going to be a positive. And then 3, this is positive, positive, negative. So that's going to be negative. Okay, so instead of looking at these, it would be nice if we had an idea of what we should be looking for. So here, if the derivative is changing from negative to positive, the function is changing from decreasing to increasing. That means we have a minimum. So we have a relative minimum at x equals -2, and then we're going to have a relative maximum at x equals +2, because there the derivative is changing from positive to negative. That means the function is changing from increasing to decreasing. If you can connect those two things, it makes it easier to see that. So relative minimum at -2, relative should be a minimum. It says a maximum. So that's out. I don't even need to check the rest, but that's probably the backwards also. Yeah. Relative minimum at -2, relative maximum. So that looks good, but I still want to check these other ones. So relative minimums at both? No, because 2 is a maximum. Relative maximum at both? No, because that's a minimum. It cannot be determined. Actually, we're pretty sure it's B. So if we have time, we want to check all of the distractors as well. Okay, moving on to our third example here. Find the graph of the derivative. So usually they tell you that, and it's labeled over here. So usually they tell you more than once if you have a graph of a derivative. So it says, which of the following could be the function f? Okay, so if you look here, what we need is the derivative is negative, and then positive, and then negative. So what we need is a function that's decreasing, and then increasing, and then decreasing. Okay? So this function is always increasing, so that's out. This function is always decreasing, so that's out. That's increasing, that's decreasing the whole way. Now, this is increasing, but it starts off increasing, but this starts off decreasing, so that's out. We need it to be decreasing from negative infinity to negative 2. So this one also, this is increasing, we're supposed to be decreasing, so that's out. So we don't just want to circle this last answer though, unless if we have time we want to think about it. So this is decreasing up to negative 2, then it's increasing from negative 2 to 2, and then it's decreasing. So that's our answer. Okay? These are all sample multiple choice questions for Chapter 3. Okay. Now, derivative of that is given by that. Which of the following values of x does it have relative maximum? So the same thing. Now, we're not going to see this until Chapter 5 because Chapter 5 has e to the x in it. But that's a derivative. So all you have to do is graph that on your calculator. So even though we haven't talked about e in our calculus class yet, really, we can graph that on our calculator. And if you do that, it looks something like this. And which of the following does it have a maximum value? So it's going to have a maximum when the derivative changes from positive to negative, which is going to be right here. So it's definitely not this. Now I don't have a scale on there, so you don't see that. But so what you would do is you would graph this on your calculator and then find the 0, which would be the coordinates of that. And that's going to turn out to be C. So you should do that. Type that in your calculator and make sure that that works for you. Okay? Here's a function. This says the rate of change of f. So the rate of change is the derivative. So we want to find f prime of x. So that's going to be 1/2. I'm doing the rewrite in my head. Think about it. That's x to the 1/2. So it's 1/2 x to the negative 1/2. And it says, what if, and maybe you want to rearrange that just a little bit, 2 over root x, 1 over 2 root x. And so it says, what if the rate of change of f is twice its rate of change at x equals 1 at c? Okay, so its rate of change at c is equal to twice its rate of change at 1. Okay, so that's 1. So if we multiply, let's see, all that equals 1. If we multiply that over there, we'd have 1 equals 2 root c, divide by 2, so root c equals 1/2, square both sides, so c equals 1/4. All right. The graph of, and this question goes back a bit further, but the function f is shown. Which of the following statements about f is false? So it says f is continuous at x equals a. Well, that's false right off the bat. Okay. Now, as far as the rest of these, f has a relative maximum at x equals a. You can have a relative maximum anywhere if you cut off the graph at a certain point. X equals a is in the domain. Yeah, there is a value for it. It's just not somewhere for it to be continuous. The limit from the left and the right are equal to each other. That's true. And if the limit from the left and the right are equal to each other, then the limit exists overall. So that's true also. So it's just right off the bat there. The graph of the function is shown in the figure over here. Which of the following could be the graph of its derivative? So if you look at this, that's the function. the function is increasing here and decreasing over here. So we need a derivative that's positive and then negative. So the derivative needs to be positive up to here and then negative after that. So if these are the graphs of the derivative here, you can see that the graph of this derivative is positive here and negative here. So again, it seems like that is right off the bat going to be the answer. Now here the derivative is positive all the time except at these little inflection points possibly here. So that derivative, that graph should be increasing basically the whole time with maybe a pause here and here. But overall, so that can't be the answer. This one, the derivative is negative and then positive. That means that the function should be decreasing and then increasing. That's not right. Here we have two changes. So here we have a positive, so it should be increasing, but then it should decrease, and then it should increase again. So that's not right. And this one, this is positive, and this is negative. But, okay, so if that's the derivative, for a second there it might look like that might work also. But let's think about the second derivative here. The second derivative of this equals 0 because the derivative of a line is a constant. It's the slope. So that means, and the slope is negative. So actually, I didn't write that right. It's not that the second derivative equals 0. The second derivative equals a constant. And in this example, the constant, the slope of that, would be negative. So, since f double prime is less than 0, it should be concave down the whole way. And this is not, this is only concave down from here to here. So that can't be right either. Okay? Now, even though we skipped 3.8, there was a good question to warm up in there. So I'll have you go back and look at that. That's on page 73. So if we go back to page 73 and we look at this and we start reading, this was on the 2003 exam, it was number 90. So it was on the calculator section, but it's not a calculator question. So you'll see that as we practice, there are questions on the calculator portion that have nothing to do with the calculator. So f has a positive first derivative. So think about what that means about f. It means f is increasing. So those are increasing. These are increasing. These are decreasing, so that can't be the answer. These are decreasing, so that can't be the answer. These are decreasing. So, well, now we're up to a 50-50 chance. That's better than... and on the real AP test, they only have 4 total now instead of 5, so that's another thing. But so we have a negative second derivative. So we have a negative second derivative. That means that f is concave down. And if you think about what that means, concave down, so you think about these tangent lines as we move across, and the slopes decrease. The slopes decrease. So we need to be checking to see which slopes decrease. So the slope between here is 9 minus 7, that's 2 over 1. So the slope between there is 2. This is 3 over 1, so the slope is 3. And here the slope is 4. So those slopes are increasing. So that can't be concave down. Here we have 4, and then 3, and then 2. So that's going to be the answer. So that was a good question. I just wanted to pop that in. Newton's method is not on the AP test, so that's why we're trying to save a little bit of time off of that. And finally, I'm going to go back and look at the optimization notes here that didn't finish because they were kind of long. So I'm going to go ahead and finish these two up. I'm actually going to do number 7 first because that relates to one of our assignment questions. I think it was number 19. Can't remember the page number, 216 maybe, number 19. So if you're having trouble with that, this will help you. So they want to design an open box that has a square base. So a square base, so you can pause this and try to do part of this yourself. Square base means those are both going to be x, and then we'll have a height there. The surface area is 147. So we can write a formula for the surface area here. That's going to be, it's an open box, so we're nothing on top. So that's just going to be x squared. And then these longer rectangles around the side, the area of each of those is going to be x times y, and there are 4 of them. So that's going to be 4xy. Okay, so draw a picture, come up with an equation, and then what it says is the box with the maximum volume. What dimensions give us the box with the maximum volume? So that's where we use a capital letter when we're trying to maximize or minimize a value. And the volume is the base area times the height. So the base area times the height would be x squared times y. So our next step is to eliminate one of the variables. We want to get it in terms of one variable. So I'm going to solve this for y. So I'm going to subtract x squared from both sides and divide by 4x. So now we can substitute that in for y into our volume equation. So we have that times 147 minus x squared over 4x. And we can cancel one of these x's here with that one. And so if we multiply that out, we will get, let's see, let's do the higher one first. So that would be negative 1/4 x cubed, negative 1/4 x cubed, and then here this looks like it's going to be 140 plus 147 over 4x plus 147 over 4. I didn't need to flip-flop that. It might actually work better the other way around, but we'll see. So now we're going to take the derivative. So the derivative of that is going to be negative 3/4 x squared plus 147 over 4. So if we factor out a negative 4/3, we're going to get x squared minus 49. And if we set that equal to 0, we'll get x plus 7, x minus 7. So our next step is to test. We don't really need to test negative 7 because the dimension can't be negative 7. That doesn't really make sense. So we'll just test positive 7. So if we plug a 6 in there, that's going to be a negative times a negative, which is positive. And here's where we want to be careful. This has come up once or twice before. As far as like dividing both sides by negative 3/4, that changes the signs of this, and that's not good. So we don't want to divide those out when we're solving like that. And if we plug in 8, those are both positive times a negative, so that's a negative. So we have a relative maximum at x equals 7 because f prime of x changes from positive to negative. Okay, so that's going to be, it's inches. So it's going to be 7 inches by 7 inches by, and if we want to solve for y, we can put 7 in right here, and that's going to be 3.5. All right. And might as well wrap up. You don't want to have that blank question in your notes, although 3.8 is blank. So if anybody really wants that, let me know. I'll take a picture and post 3.8 if you feel the need to fill in your notebook completely. All right, so this is a little bit of an awkward question, but I still want to do it anyway. So an apple orchard, there are 30 trees per acre. and the average yield is 400 apples per tree. For each additional tree per acre, the average yield of the tree is reduced by 10 apples. So the more trees you try to pack on there, that's going to take more of the water, blocks more shade on, so there's going to be less apples per tree. So you want to try to find that best balance of what you're going to do. So the question says, how many trees per acre will maximize the crop? So the trickiest part here maybe is deciding what the variable is going to be. So I think what I want to use for the variable is each additional tree. Now I didn't really pause for you to think about that, but hopefully you're using the pause button. So T is going to be the trees added, the number of trees that we're going to add. Okay, so maximize the crop. So I'm going to use C for the crop. Okay, so we're going to have C of T. Okay, so we're looking at two things here. We're looking at the number of trees, and we're looking at the yield, or the apples per tree, to tell us how many apples we'll have, right? So the number of trees, we started with 30 an acre, so we're going to have 30, and we can add trees if we want to. And the yield of the trees starts off at 400. So if you think about it, I didn't talk about the domain again, but I didn't talk about the domain number 7 either. But the domain, it might be best not to add any trees at all. So we might not want to add any trees. Now, if we add, we're losing minus 10 per tree. So minus 10 apples per tree. Now, if you think about it, if we add 40 trees, that would be minus 400. That'd be there's no apples. So that doesn't make any sense. So that would be our upper limit. Doesn't even make sense to put a bracket on it though, because we're trying to grow apples, and we're going to get 0 apples per tree. That's probably a bad idea if you're trying to sell apples. Okay. So we could do our candidate table. So we could do trees, and we have 0, and then we could have the crop. So if we don't plant any trees, we'd have any more trees. We'd have 30 times 400, that's 12,000 apples. Okay? And if we plant 40 trees more per acre, so 70 trees per acre, we're not going to get any apples. So obviously that would be silly. Okay, so if we go back, now we could multiply this out, but we could also just use the product rule. I'm not really sure which one's faster, so if you want to try the product rule, you can, but or if you want to try to multiply it out and take it, I'm just going to use the product rule. So the derivative of this is 1. So I guess I'll put a 1 there. 400 minus 10t. Plus, the product rule says the first thing times the derivative of the second thing. So that's negative 10. Okay, so just clean this up a little bit. We have that, and distribute here. So that's going to be minus 300 minus 10t. We're going to set that equal to 0. We are going to probably move all this, well, we don't have to, I guess. I was going to move it to the other side, but that's going to be 100 minus 20t. So we could factor out a 20 and get 5 minus t. So that's going to be 5. And if we test it out, if we plug in a 4, we're going to get positive and negative. So that means we have a relative maximum at t equals 5 because c prime of t changes from positive to negative. So we can plug a 5 in here, and if we plug in 5, that's going to be 35 times 350. 350 times 35. 0, 25, 15, 16, 17, 0, 15, 9, 10, 0, 5, 12, 12,250 apples. So how many trees per acre? Now here's a little bit of a trick. Now don't say 5. You have to, it says how many trees per acre. There were 30 already, so it's going to be 30 plus 5. So that's going to be 35 trees per acre. Okay, it's another real world application if you're figuring out stuff. All right, it's about that time. See you later.